Dear students, in previous lecture we discussed salient pole type rotor of synchronous machine. Now we will discuss non-salient pole type of rotor used for synchronous machine. This rotor is also known as cylindrical rotor. So we may write non-salient pole rotor or cylindrical rotor of synchronous machine. A generally two pole rotor is used, sometimes four pole. So a two pole non-salient pole or cylindrical rotor of a synchronous machine is shown in figure. This is also assembled with steel laminations. Generally the materials used are chromium nickel, steel or chromium molybdenum steel laminations, in which slots are pointed out as shown. Generally 1/3 portion of some circumference is left unslotted, means 2/3 are slotted. For a representative case I have shown few slots, but in practice 2/3 of the circumference is slotted, 1/3 is left unslotted for economical reason, as it is not going to affect much in reduction of flux, but it saves the cost of rotor significantly. Here we may observe that field winding conductors are placed in various slots. So the field winding is distributed in a space in a number of slots as shown. In previous case salient pole rotor we have seen that concentrated field winding was used, but here we are using distributed field winding, means field winding is distributed in several slots. Why, we will discuss later. There in salient pole rotor we observe that air gap is non-uniform, but here air gap is uniform. This is rotor, then air gap will be there and then a stator will be there, right, a stator part, a stator. So this is air gap, so we have uniform air gap, but our requirement is to have the MMF wave shape of field in the air gap of sinusoidal nature. So in order to have flux density B, that is flux sinusoidal, which is given by MMF upon reluctance. So as air gap is uniform, same length throughout, so R will be uniform. So in order to have this phi of sinusoidal nature, we must have MMF, which is nothing but Ni. In case of DC, denote with capital I. MMF is capital I, that is capital I upon reluctance. So once reluctance is fixed due to uniform air gap, this must be of sinusoidal nature in order to have flux of sinusoidal nature, that is flux density B of sinusoidal nature. So how to make this Ni of sinusoidal nature? See, we have already discussed that in synchronous machine DC field winding is supplied with DC supply, that is DC supply is given to the field winding, hence current will be constant. So this is constant, current is constant, reluctance is constant, current is constant. So only left option is with number of turns. So we are going to vary number of turns in different slots in order to get sinusoidal flux density distribution in the air gap. How? let us take any slot. Suppose we have number of turns as 3 here. So diametrically opposite slot is this, that is 3 turns, that is 3 is here, right. We have number of turns. Suppose we are just taking a representative case, any number you can take. Suppose 3 we have taken here. Let us take here some different number, let us take 7. So diametrically opposite 7, right. Now here let us increase again 10. So we will have 10 here. We know that a conductor carrying current produces field flux. So flux direction may be obtained with the shown polarity. Dot is there out of the plane. So let us take this coil having 3 number of turns. So flux direction will be take right hand and curling of the fingers means this way, somewhat this way. Again 7 somewhat rotated anti-clockwise, again this somewhat again rotated this. But strength will be more in case of 10 number of turns than in case of 7 number of turns than in case of 3 number of turns. So in such a way we will get some stepped output like this, a stepped wave shape. Let us take one axis here. So here let us start from here where we have 10. So we can start from anywhere. Again if we are again suppose putting 10, why we are putting equal we will explain later, discuss later. Again have the same similar 7, then 7 here, opposite also 7 here, then this was 3. Okay. So how many slots we have? 1, 2, 3, 4, 5, 6 here, 1, 2, 3, 4, 5, 6. Okay. So one more we have unnecessarily made. Fine. So 3, 7 and this will be 3, then this will be 3. So let us mark this point as reference point, 0 point, origin. So start this position in a space. So we know that when one complete rotation makes 360 degree. So starting from 0 degree, this is 10. So corresponding to 10, flux distribution will be, direction of flux will be here at this position, not at this position. Corresponding to this, so corresponding to this position, what will be flux distribution? See, if we are having some coil here and here, so flux direction will be here. So as of now we don't have any slot, no conductor, no current, so no field in this direction. So that's why we have marked some 0 here, from here till here. It will be more clear. Let me draw it first. So for 3 we will make 3 steps, horizontal, then so we have moved till here. So this is corresponding to this point till this point, 180 degree. This is 180 degree. You may write pi. So let us extend it further. So this point is corresponding to this point. See, we can observe that flux density is more here at this portion. Why? Because the coil having maximum number of turns, let us say 10, this dot and this cross, will produce flux in this direction. Similarly, this other one, this 10 and this 10, right? We have taken this 10 opposite, now take this 10 and this 10. So both are producing flux distribution maximum in this portion, in this region, and this region is, if we are starting 0 from here, so 0 around 90 degree. So the region from 0, this is pi by 2 somewhat, pi by 2, the portion 90 degree will have maximum flux density corresponding to these number of turns 10, and in between, see, the effect of 7 will be there, direction. So density will be lesser than this. So this is corresponding to 7, this is corresponding to 10, and you mark this is corresponding, this magnitude is corresponding to again 3. We are moving in this region. So in this region, this is 3, this is 3. So corresponding to 3 number of turns, the density will be lesser here. So we will mark 3 here, right? We may mark here flux in the air gap. Again, after 90 degree, what will happen? Again, we are reducing the number of turns in the slots. Say after 10, 7 is there, so it will be lesser. Again, after this 3 is there, so in this region it will be lesser. What about in this region? So no turn in this axis. So here again we will have 0 flux density distribution. Now again move to this third quarter, right? We may mark here like that. Like that. So we have talked about first quarter from here to here. So you mark first quarter from here till here. Now come to the second region, second quadrant or quarter, whatever. So this is second from here till here. So what about third and fourth? So again in third and fourth quarter, you may see that as the number of turns are also having similar number of turns as those earlier. So we will have wave shape like this. And this will be 2 pi. Again we have reached till this point, 2 pi, fourth, right? So this region will be corresponding to, this is 3 pi by 2 and 2 pi. So this is corresponding to third quadrant and this is corresponding to fourth quadrant. Try to observe this distribution, flux distribution in the air gap. As air gap is uniform, reluctance is uniform. So in order to have varying flux density distribution in the air gap, we have varied number of turns in various slots. How? The slots near to interpolar region. See, if we are going to create north and south pole by providing the direction of field currents, dots in this region, cross in this region, you know, right? We have coils and we have DC supply plus minus. So we may create wherever we want dot, wherever we want cross, right? So we have created north pole here, south pole here by energizing the field winding as shown, dot here, cross here. So this will be polar region, right? North pole, south pole, and this will be interpolar region. So we can say that by varying number of turns in the various slots in such a way that the slots near to interpolar region are having highest number of turns, and we are decreasing subsequently, we are decreasing the number of turns in the slots subsequently as one moves from interpolar region towards polar region, right? 10, 7, 3, or we may have several number of slots. So we may observe here that this approximates a sinusoid, not pure sinusoid. We will never get pure sinusoid distribution, right? But we can say that this approximates some sinusoid, something passing through 2 pi, something sinusoidal. This nature is somewhat sinusoidal. Although a stepped wave output, we are getting a stepped wave output. So we will never get pure sinusoid, but by increasing number of slots, we can increase such steps. So if we are going to increase slots, so these steps will be smaller and smaller. It will resemble its shape closer and closer to sinusoid, though not pure sinusoid. For pure sinusoid, we need to have our number of slots infinite in number, that is not possible, but we may have very large in order to create near to sinusoidal wave shape. Hope it is clear to you. So, what is the drawback of having not pure sinusoid? It will have harmonic components. Apart from fundamental component, it will have harmonic component. So, what will be effect of those harmonic components? See, remember again, field winding is energized with DC supply. By an special arrangement, we have created near to sinusoidal flux density distribution in the air gap. Repeating again, in case of non-salient pole rotor, that is cylindrical rotor, we have distributed field winding, air gap is uniform. In case of salient pole rotor, in previous lecture, we had concentrated winding, not distributed, but air gap was non-uniform. So, in the two cases of salient pole rotor and cylindrical rotor, by spatial arrangements discussed separately, we have made our flux density distribution in the air gap close to sinusoidal. So, once rotor is rotated at synchronous speed by means of any prime mover, what will happen? Windings will also rotate with rotor. So, these wave shapes will also rotate at the same speed. These wave shapes will link to the conductors placed on the slots cut on the inner periphery of stator winding, that is 3-phase stator winding conductors, resulting in induction of EMF in the 3 phases of the stator winding. Those EMFs will be having harmonics because of harmonic content in this wave shape. These wave shapes, field MMF wave shapes, are having fundamental component and harmonic components. Similar to that, the EMFs induced in the 3-phase windings will have fundamental component and harmonic components. So, these harmonics are required to be suppressed. That is why short corded windings are used to reduce these harmonics. Even 3-phase star connection is used. Remember, note down, for alternator 3-phase synchronous generator, the stator windings are always connected in a star in order to, just point number 1, reduce third harmonics, right? It will kill third harmonics. Remove, you better write, remove third harmonics. Point number 2, neutral point will be available in a star. And point number 3, you may write that it reduces the insulation requirement of a stator winding. How? For any line voltage, required line voltage, just we need to generate phase voltage magnitude, this which is 1 upon root 3 times line voltage. So, if phase voltage is to be generated is reduced by 1 upon root 3 times, it means corresponding conductors will be reduced, corresponding insulation will be reduced. So, due to economic reason also, we prefer to use a star connected stator windings rather delta. So, always we are using a star connected stator winding. Fine. So far we started this subject with introduction of construction, though not so interesting, but wait, later we have lot of topics in this which will create you hopefully much interest in this subject. So far, but it is required to have the idea of construction, why your rotor is like this and this, why we are having 2 type of rotor, what is the reason behind that, using distributed winding and like that, right. So, in brief, we can say that for high speed application, non-salient pole rotor is used, that is cylindrical rotor is used, mostly 2 pole where speed is very high. For 50 Hz 3000 rpm, right, for 60 Hz 3600 rpm, whatever you can calculate, right. At max we can use for 4 pole where For 50 Hz, 1500 RPM speed will be there. For low speed applications like hydro turbines or like that, these high speed applications will be generally in like turbo generators, right, steam turbines. In hydro, where this height is very low or discharge is very low or like that, right, where we need a small speed in a smaller range. So, there we will prefer the rotor with large number of poles, that is salient pole rotor. So, we have now generated EMFs in the 3 star connected phases of a stator winding. So, we can represent this neutral point like this, and these are the output terminals of a stator and corresponding currents IA, a small notation for instantaneous value of current, right, IB and IC are collected by 3-phase load. We have another excitation on field winding, rotor, on rotor field winding. So, we may say this RF and this is plus minus, corresponding current may be represented IF, field current, right. You may write VF, DC supply is provided on field winding, right, and this whole part is rotated by means of prime mover, say in anti-clockwise direction at any synchronous speed omega s or omega whatever in radian per second, or in RPM you may represent, right. So, this assembly is rotating and this is a stationary part, a stator, you may write rotor here, this is a stator and collected. So far we have a small idea of this, we have started with this. Now, the interesting topics are awaiting for you. So, first we will discuss armature reaction next to this lecture and the remaining topics, right.